This is the pre-lab talk for experiment number 13 for Chem 120 lab, complex ions. This experiment has two parts. The goal for part 1 is to observe solution chemistry that involves precipitation and complex ion formation. In part 2, we'll use what we learned in part 1 to positively identify metal cations in an unknown solution. For today's safety pause, we'll note that at 3 molar concentrations, sodium hydroxide, sulfuric acid, and ammonia are moderately corrosive. We'll also note that ammonia at a 3 molar concentration can also give off fumes. To mitigate this risk, we store the ammonia, aqueous ammonia, in a dropper bottle, which allows us to limit the amount of ammonia that is being dispensed. Aside from being an environmental hazard, KSCN, potassium thiocyanate, can combine with certain oxidizers to produce a gaseous product that has an unfavorable odor. All chemical waste for this experiment will be collected in a designated waste bottle. And of course, we'll remember to wear our personal protective equipment, our safety goggles, and a flame-resistant lab coat. In this qualitative analysis experiment, there are several types of phenomenon that we can observe occurring in solution. The first deals with solubility equilibrium. You might have learned in lecture that for a compound that is generally described as being insoluble in water, according to our solubility rules, has a very small solubility product constant, or KSP value, and is generally very unfavorable to dissolve in water. However, if we reverse the reaction to describe a precipitation, then our equilibrium constant, which is the reciprocal of the KSP, will be rather large. Therefore, precipitation reactions are major driving forces. They are very highly favorable in aqueous solution if the conditions are just right. In this lab, we'll also take a small look at amphoteric behavior. Amphoteric compounds are compounds that can act as an acid or a base depending on the conditions. For example, zinc hydroxide, which is an insoluble solid, can act as an acid as it picks up additional hydroxide ions to form a complex ion. More on that later. And it can also act as a base with the hydroxide ions that are part of the solid. Zinc hydroxide will react with any acid in a double displacement fashion. A perhaps new part of chemistry we're going to look at in solution are the formation of complex ions. Complex ions form as a result of a Lewis acid-base reaction. A metal cation acts as a Lewis acid, which is defined as an electron pair acceptor, and will accept these electron pairs from the Lewis base. We also refer to Lewis base in our complex ions as ligands. When a Lewis acid combines with a Lewis base, we form an adduct. And in this case, our adduct will be the complex ion. There is a lot of competition between the various types of equilibria that occur in solution. For example, we can see on the right that we have 3 equilibria involved in the observations that we're noting here. First of all, when we add ammonia to water, it can undergo base ionization to form the ammonium ion and the hydroxide ion. The hydroxide ion can also then react with the copper 2 plus in the solution to form a precipitate, which you can see in the left picture. However, when an excess amount of ammonia is added, then a complex ion forms between copper 2 plus and the ammonia ions, or ammonia molecules. The observation that this complex ion is forming is the color change from a light aqua blue color to a deep royal blue color, which can be seen in the right-hand picture. We will see a lot of these types of transformations as we carry out the reactions in part 1 of this experiment. For this experiment, it's important to note that there are going to be 3 possible outcomes for each reaction that we perform. The first outcome is that you can observe a precipitation reaction, the formation of a solid between 2 clear solutions. The next 2 observations are related to the formation of a complex ion. You'll know if a complex ion is forming if one of the following 2 things are true. You can observe a straight color change, perhaps without the presence of a precipitate. This would just be a simple observation of a color change. Another thing to look out for is the formation of precipitate that redissolves after more of the reagent is added. This indicates the presence of a complex ion forming, which is competing with the formation of the precipitate. The complex ion formation is more favorable than when more reagent is added. Let's look at a couple other procedural points as you watch the lab video. In the lab video, you'll notice that the directions in the experimental are followed very carefully. Reagents are added dropwise. Up to 20 drops or more of the reagent is added to each solution to make sure that all observations are recorded. Again, sometimes you'll note that after a precipitate forms, it might redissolve to form a clear solution, indicating the formation of a complex ion. So it's very important as you note the observations to record all observations after each addition of reagent. As you're doing this experiment, it is important to pause after recording observations for the 20 reactions and complete questions 1 through 3. These questions allow a bridge between part 1 and part 3 and allow you to narrow down specific tests that can be performed in order to identify metal cations in the unknown solution. It is also important to note that in part 2, we are using more reagent than we are in part 1. This is because in mixtures of different cations, it is important to add enough reagent so that it reacts with all of the reagents, all the cations that might be present in the solution. Okay, I hope you guys enjoy the video with all of the reactions. I certainly enjoyed making it for you guys.